Hello class, this is CIS 170 Operating System Concepts. My name is Glenn Scheneman and I will be your instructor throughout this 8-week ADP course. First thing I'd like to do is get to know the class. So for the on-ground students, I'm just going to pause the video in a second here and have everybody go around and introduce themselves so I can get to know you better and you all can get to know each other better as well. For the online students, I would like you to write a forum post, and I would like one response to that forum post in e-learning. For week 1, you will see this. This is for online students only. It's very clearly identified. So if you have any questions, let me know. But if not, I'm going to go ahead and do the Meet the Class section now. Thank you. Now we'll continue with an introduction. An operating system is a program that manages the computer's hardware as well as its basic functions. And operating systems at their core perform basic computer tasks. So what are some of these tasks? There's the task of the operating system, there's recognizing and installing peripheral devices, managing files and folders. You have to look at the sharing out of memory. You have to talk about the handles and error alerts. We're going to talk about how it manages system security and how it allows software to communicate with the hardware. We're going to understand how it moves data from the hard disk to and from the hard disk, and that it loads and runs other software applications. And last but certainly not least, it handles inputs and outputs. So all of these items here are the tasks of pretty much every operating system, and we're going to focus on different tasks of the operating systems as the weeks proceed here in this class. Thank you. So to continue the introduction, operating systems are designed to be convenient or efficient or a combination of both. So that's an interesting thought. So what that means is that some operating systems are convenient, meaning they're super easy to use. They've got a lot of extended features that you wouldn't necessarily need, but it's very convenient and easy to use. That's the concept behind the Windows operating system, or even the graphical user interface in OS X. So I'd like you to review computer security, identify input and output devices. And we need to understand that operating systems are large and complex. So at this point now, I believe I'm going to have the online students write another forum post identifying input and output devices on a computer. So when you look at things like a printer now, for example, be careful, because a printer can be an input device because it can send a message to the computer saying, hey, I'm out of paper, hey, I'm offline, I'm out of toner. So it can be an input device, but it can also be an output device, and it's an output device when it sends a report to the printer. So I'd like you to put some thought to that. Obviously there's the keyboard, the mouse, there's this microphone that I'm using right now, so all kinds of stuff. But I'd like you to write a forum post identifying quite a few pieces of input and output devices, and that will be in e-learning as well. So to continue on, a computer system consists of 4 primary components. There's hardware. They all have an operating system. They all have application programs, and computers need users, whether it's a single user or many user. So operating systems, it's important to understand that they provide the environment. So we'll continue on. So there's the user view, and this is the way the user sees the computer. It could be a smartphone, it could be a workstation, it might be an old banking terminal. So it could be all kinds of different views, and the operating system maintains and manages those views. Next we'll discuss the system view. This is how the computer sees the computer system. And for the operating system, resource allocation is essential. It's one of its primary responsibilities. So it allocates and maintains computer resources. Some of these resources include CPU time, memory available, file storage space, and then there's other I/O devices. So the CPU time is the amount of cycles or the amount of processing time that the CPU has to handle a certain task or process or job. So when you see your computer sitting there hanging really bad and it doesn't seem like it's working or anything, that's because there isn't a lot of resources available in regards to its CPU time. Memory available, after a while you can get the same kind of issue with memory when you don't have any available random access memory. You have file storage, resource allocation. That's really talking about your disk drives, whether they're network drives or whether they're local disk drives. And then there's other I/O devices. That could be things like your keyboard, your mouse. You were writing a forum post on that, and we've probably discussed that by now in the on-ground class. So now we'll talk about control programs. They handle the execution of application programs to prevent errors and improper use of the system. So devices such as printers and keyboards are controlled by device drivers. So we're going to be discussing that in Windows, and you will see some of these device drivers when we go through Linux as well. With device drivers, we're primarily going to focus on Windows. It's a little more graphical. If you're going to be using a school's computer for this, the access to the device drivers will be somewhat limited, but we will discuss them, and we will point out where these device drivers are located and how they operate. This is going to be a very hands-on class. So control programs also manage system usage and application programs. So now we need to define operating systems. So there is no true adequate definitions. Different operating systems do different things. Operating systems create usable computing systems. A computer without an operating system won't do anything at all. It'll just come on, and you've actually maybe seen that before. If you don't have anything to boot to on a disk or something, it'll just say not found, and that'll be just about it. There's many different vendor packages that deliver many different operating systems. There's commercial products such as Microsoft. They deliver Windows 10. They also deliver Server 2012, they deliver Server 2008, as well as a bunch of other smaller bundled up operating systems. So Microsoft is a commercial operating system vendor. Then there's going to be other types like Solaris Unix, maybe AIX by IBM, that's a version of Unix. So those are also proprietary and commercial products. And then there's also commercial versions of Linux out there, and there's free and public supported version of Linux. So Linux is open source, and that's the main thing to remember here, where Microsoft is not. You do not get to see the code that Microsoft provides, where with Linux you get to see absolutely all of the code that they provide. So operating systems, maybe we could define it as a necessary program that always runs on the computer. And this necessary program is referred to the kernel. Now there's a lot of programs that assist the kernel, but the kernel is the main operating system program, and that frequently gets updated, and when it does, it's a big undertaking. So we'll look at computer system structure. So most modern computers have the following: one or more CPU. When you hear of a core, that's a CPU. Device controllers. We've talked about the controllers for the devices. There's the bus. That's the channel that controls all the traffic between the different devices and the input and output devices, and as well as RAM, as well as the CPU. And then there's shared memory, which consists of RAM and ROM. So RAM is read-only memory, or I'm sorry, ROM is read-only memory, which means that what's in ROM can only be read. You can't write to ROM. That's not 100% true, but for the most part, a ROM is set in stone. Where random access memory, if you turn your computer off, it goes away. It's totally random memory. Thank you. Now we're going to go through the various parts of the computer system to kind of go over what we discussed on the last slide a little more. So you have your memory, whether it's read-only memory or ROM, or random access memory, which, like we said, that's memory that's volatile, and ROM is not volatile, which means when you shut the computer off, the memory that's in RAM will go away. Some operating systems run out of ROM. For example, if you remember the Commodore 64, it had an operating system available to it within 5 seconds after you turned the computer on, and that's because the entire operating system for the Commodore 64 was stored in ROM. Whereas with a Windows system, everything gets loaded into memory when the computer is turned on. The operating system is stored on a disk and then gets loaded into RAM, and that's how the computer's controlled. The CPU handles the instructions that are provided by the RAM or the ROM, and it will read from the disk controllers, which control the disks. It may read or send output to USB controllers or the graphics adapter as well. So your graphics adapter is a device driver, and it controls the monitor. So in most cases, monitors are really going to be only output devices, and keyboard is pretty much always going to be an input device, and disks can be input or output. So this is a basic general picture of how your computer looks, and I believe in Professor Concepcion's class they went over this a little bit, which I believe is a prerequisite for this class. So you should have an understanding from your Intro to Computers course explaining how the computer works, and as computer professionals this is something you should know. So now we'll go on and we'll discuss the Bootstrap program. This is stored in the EEPROM, which is a firmware or ROM. We'll just call it ROM for simplicity's sake right here. A Bootstrap program is the program that starts up when the computer is turned on. So on a ROM for a PC, you start it up, it's going to have some settings that you can configure, and it's going to say this is where the disk drives are. This is what I want you to start first. And then the disk drive itself will have its own Bootstrap on it, which will know where the kernel is for the operating system and know where to go get it and know where to start it up. So once the kernel is loaded, then other system processes and helper programs will work along with the kernel. So these are referred to as processes or daemons, and we can see a lot of those as we go ahead. So if you don't fully understand this yet, don't worry, we will discuss it more as we go through our hands-on work, which is how I prefer to operate anyway. But that's an important thing to remember. So now we're going to talk about interrupts. There's hardware interrupts, which are examples such as the printer running out of paper, a mouse click, a hard disk signaling that it has read or written data, a network device signals that it may have received packets or sent packets. So these are physical hardware occurrences that trigger interrupts, where software interrupts are triggered by system calls or software for the most part. So when a program ends, you end Microsoft Word, it sends an interrupt to the operating system saying, hey, Word has ended. Same thing with starting Word or any other program. If you wanted to open a file in Word, that would trigger a software interrupt as well. So just keep in mind, I was using Word as an example, but it's going to be with any type of software that's run can trigger a software interrupt. Now we're going to talk about storage structure. We're talking about memory and secondary storage. Most computers run their programs from memory. Bootstrap programs are run from ROM or EEPROMs, which is really just a type of ROM. So what that really means is a Bootstrap program is what goes out and looks for the operating system. So this program is the default program that starts up when the computer is turned on. So operating systems and other application programs are run from main memory called RAM or random access memory, and that's volatile. So like we said before, volatile memory is memory that goes away when the computer's shut off. So anything that's loaded into RAM has to be loaded from someplace else. Usually that someplace else is secondary storage, and most of the time it's your disk drives. So secondary storage must be able to hold large amounts of data and be non-volatile, meaning when you turn it off it will not go away. So that's what you see. I mean, you turn your computers off now, you turn them back on, all your old documents are still there, your operating system still comes up. So it's non-volatile for the most part. What was originally on your system stays on your system, and what's started on your drive will stay on your drive. And some examples of secondary storage include hard disk drives like your C drive. It can also include network drives once it connects up, and jump drives or flash drives, and PDAs. So when you're reviewing these slides on your own, and you should be reviewing them on your own, follow this link here from techterms.com and get an understanding of what a cache is, and that's pronounced cache, not cache. In short, it stores recently used information so it can be retrieved quickly. So I'd like you to understand what a browser cache is, and most people who do web surfing do understand what a browser cache is. I want you to learn about the memory cache, the disk cache, and the processor cache. Okay, thank you. So do look into this. Next, I would like to discuss single core versus multi-core systems. So this video here, which we'll watch in a couple minutes, gives a really good example and understanding of that. If you wanted to watch it outside of these slides, this is the URL and the link to it. Multi-core processors can have multiple CPUs, and they're called cores. On one chip, the system can have multiple CPU chips. So the advantages are improved throughput, improved cost, and increased reliability. But without further ado, we will go in and watch this video now. Thank you.
Hey guys, Woody the Unexceptional Gamer. Time to clean off the whiteboard, break it out, because this is Technical Tuesday, a weekly series where I teach you something new about tech stuff that perhaps you didn't know before. So, one of the ways I pick the topics is what you want to see. And one of the highest rated comments from last week was, why have CPUs moved from gigahertz or single core over to multi-core? What made them make that decision? Why is that better? Why is that worse? And I thought, let's break that down. So there's a bunch of ways to make CPUs go faster. One way is just to take the same darn CPU and increase the clock speed. You've probably heard of, this thing runs at 1 megahertz, this thing runs at 4.5 gigahertz and stuff like that. That's just how many times per second your CPU is doing something, doing anything. In my lifetime, I've seen computers go from 1,000 operations per second, which is the very start, Apple II, to 4.5 million things per second. So just doing more things per second is one way to make a CPU faster. Another way that we'll barely talk about in this video is to make each of those operations do more complicated things. For example, if I wanted to tell you do 5 times 5, then you could have a bad CPU that takes 5 and adds it to 5, 5, 5, 5, 5. Or you could take a great CPU that has transistors built in it that have operations, that have times tables built into it, and boom, 5 times 5 is 1 operation instead of 6. So that's 2 ways to make the CPU go faster: by making each operation count for more, and by making more operations happen per second. Semiconductor engineers are pretty smart people. They would use all of these techniques, but there was a problem with the frequency ramping up, and it's that it ran hotter and it used more energy. As they went from 1 gigahertz to 2 gigahertz, it didn't just double the energy consumption, it tripled it. And then as it was from 2 gigahertz to 3 gigahertz, these aren't exact numbers, but they're roughly right, it doesn't just go 50% more for the 50% more performance you might get, it quadruples it. And as the thing runs hotter, you start to get the expansion, the transistors in the CPU can touch, and there you see on your screen, ouch, things break. Just ramping up frequency was no longer the best way to get more performance. So along comes this idea of sticking multiple CPUs on one die, and you've got your multi-core CPU. I'm about to draw you a 4-core CPU. And what they figured out was, you know what? It is better, it is cheaper, and it is faster to stick 4 cores on a CPU compared to just having 1 that runs super fast. So 4 at 3 is way better than 1 at 6. Mostly. The reason I say mostly is that not all jobs lend themselves to being done in parallel, to operating on each of those 4 cores at one time. So I'm going to show you an example of a job that nicely breaks down into parallel processing. It's a video thing. So imagine you're looking at a picture. The picture's just a row of pixels, right? So here's what I have here, the world's ugliest picture. And then you wanted to take that picture and rotate it by 90 degrees. This is something that easily translates into a multi-core job. All you have to do is take the top row of pixels, make it the right column of pixels. Take the middle row, make it the middle column, and so on. That's how you would do it on a single processor. Now, let's imagine we're going to do this thing on parallel processors. We're going to get clever on this thing. Instead of just taking the row and shifting it, we're going to break it into two separate jobs. And as you watch me draw this, keep in mind, I operate in serial because I'm only a human. But if you were to take this in two jobs, now we have one picture, slice it up, and we're going to take that top row and do it there, and then take the next one and put it there. And you can kind of see what's going on here. We have two jobs operating on this picture at the same time, and then when it's all finished, we can combine it and we'll be good to go. In the world of video processing, whether you're making videos like I do, or whether you're creating video games or just manipulating video, there's a lot that you can do in parallel, right? There's a lot that you can do to fully take advantage of the 4 or 6 or 2 cores that your CPU has. However, there are certain kinds of jobs that don't lend themselves to being done in parallel. There are certain kinds of jobs, and they're mostly like if-then kind of problems, right? So I'm writing some code here in front of you. If you're not used to reading code, it pretty much says, if Woody is awesome, click like. If Tech Tuesday is cool, then click like. If you are a troll, click dislike. There's a problem with this kind of code, and it's that you can't really just put it on 4 different processors and have it run. I wrote it like this for a reason. This is a step-by-step set of instructions, and if you were to try to get ahead of yourself like you could with that rotating picture where I can just say, hey, take this, divide it in 2, and you both handle it at once, you already know how that's going to go down. This is an if-then thing. If it requires user input, or if it's like rendering an HTML page where until you know what the bottom of it looks like and the top of it looks like all put together, you don't know what that page is fully going to look like. Some things just happen in serial. Some things just happen one at a time. So having 2 cores is not perfectly better than having 1 core. You know, having 2 1 gigahertz cores is probably not as good as having 1 2 gigahertz core, because that 1 2 gigahertz core, assuming all else is equal, will be twice as fast in every scenario, whereas the dual half speeds will only be as fast in certain scenarios like rotating pictures that naturally lend themselves to multi-core processing. So that's it in a nutshell. That's the pros and cons and the why CPUs now.
And lastly, this week we'll discuss the timer. So timers are used in operating systems to ensure the control of the CPU is maintained. This prevents programs from getting stuck in an infinite loop and just running out there for hours and hours, or forever actually, without ever stopping. Timers can be variable or fixed, which means you can either set the timers and have it be programmed something you specify, or it can be a fixed setting. An example of a timer that I like is when you have a program in Windows, which I know we all have, that's been hanging out there. After a minute or so, it'll pop up on the screen. It'll say in the menu bar, it'll have the name of the program. It'll say not responding next to it. And then shortly after, you have the option to terminate or to continue. So these kind of things are useful to make sure that the program actually is stoppable and that it doesn't just run forever. So timers control that sort of thing. Hopefully that makes some sense to you. Thank you.